Have you ever wondered why some structures fail suddenly, leading to catastrophic collapse, while others provide clear warning signs? In this comprehensive lesson, we'll delve into the fascinating and critical world of structural failure modes. We'll explore the various ways structures can fail and understand the ingenious methods engineers employ to design buildings and bridges that prioritize safety. By the end, you'll grasp common failure modes, why ductile failure is preferred, and how this understanding ultimately saves lives. So, what exactly constitutes structural failure? It occurs when a structure can no longer safely carry loads, loses stability, or becomes unsafe. Failure doesn't always mean dramatic collapse. It can manifest as excessive cracking, large deflections, or sudden localized instability. Engineers study failure mechanisms to meticulously prevent them through robust design and construction practices. One frequently encountered mode is flexural failure, or bending failure. This happens when a structural element bends beyond its capacity. Imagine a beam under load. The tension zone, typically at the bottom, will crack first as the material stretches. As the load increases, the compression zone, usually at the top, will eventually crush. Flexural failure is generally ductile, providing ample warning signs, large deflections, visible cracks appearing gradually. This predictable, warning-laden behavior is precisely why ductile flexural failure is the preferred mode in structural design. In stark contrast, shear failure is far more dangerous and often sudden. It occurs when internal shear forces exceed capacity. Instead of gradual bending, you'll typically see diagonal cracks forming abruptly. Unlike ductile flexural failure, shear failure is brittle. This means it happens with little to no warning, making it incredibly hazardous. Engineers provide stirrups, reinforcing bars, limit shear stress, and apply higher safety margins to prevent brittle failure. Buckling failure is primarily observed in slender columns and other compression members. It's insidious because a member can fail due to instability. Key factors influencing buckling include the member's length, cross-sectional shape, size, and end conditions. Buckling is often sudden and catastrophic. Rigorous stability checks are paramount to prevent this dangerous mode of failure. The way materials behave under stress is fundamental. We categorize material failure into two main types, ductile and brittle. Ductile failure is characterized by large deformation before fracture, significant energy absorption, and clear warning signs. Brittle failure, on the other hand, involves sudden fracture with little to no deformation and minimal energy absorption. Imagine glass shattering instantly. Brittle failure offers no warning and is extremely dangerous. Engineers aim for ductile behavior, especially in seismic regions. Structural failure isn't confined to the superstructure. The foundation and underlying soil play an equally critical role. Foundation failure can manifest as excessive settlement, bearing capacity failure, or sliding and overturning on sloped sites. Even a perfectly designed building can fail if its foundation is compromised. This highlights thorough geotechnical investigations. How do engineers prevent these failures? It's a multifaceted approach. They employ safety factors, multipliers applied to design loads. They utilize limit state design, a modern approach considering various failure conditions. Crucially, they ensure failure would be ductile. Engineers rigorously follow design codes and standards built upon decades of research and real-world experience. Continuous inspections and quality control throughout construction are vital to ensure the structure is built as designed. Good design anticipates how a structure could fail and actively controls that failure to be safe and predictable. To summarize, structures can fail in many ways, from flexural bending to sudden shear or buckling. Some failures are sudden and dangerous, while others offer crucial warning signs. Engineers design and control failure, ensuring that if it happens, it does so in a predictable and safe manner. In our next lesson, we'll delve deeper into load types and how different forces contribute to these failure modes. If this video helped you understand structural failure, please give it a like. Subscribe to Kussitta CENG Solutions for more engineering insights. Comment below which failure mode you'd like us to explain with real-world examples.
Kussitta CENG Solutions. Engineering made simple and practical.